jumping ring demo. What I have is a 120 turns coil, an aluminium ring, a retort stand that is usually got some steel or some iron in it, and a power supply. And simply, if I turn it on, 12 volts AC, we can sort of see that the ring jumps up and sort of suspends there. We notice it jumps up greatest when we turn it on. So by Faraday's law, the rate of change of current and the rate of change of magnetic field that's happening inside the retort stand is inducing change in magnetic field in the ring, is causing a current to flow in that. By Lenz's law, that's opposite to the direction in which it's been induced. That's just tripped out. Obviously, if I use a higher voltage on the power supply, then I will get it to jump slightly higher, but not too much due to the resistance of the coil. What's also quite interesting is if I try it on DC. If I try it on the DC, in theory, nothing should be induced and we get no movement. But we can probably see a little bit of vibration happening on that. That vibration is due to the fact that we don't have a perfectly smooth DC power supply. What's then useful to show to students is what happens when we now put a split ring or laminated ring on the stand and turn it on. Nothing happens. So, using a bicycle wheel axle and then an aluminium plate that has been centered so that it should freely rotate without too much friction. When I get this spinning, one of the things I can do is get it up reasonably fast just by spinning it from the middle. If I now bring a large Alco magnet near it, one of the things I can see is Lenz's law directly. So what has happened is, as shown by these little arrows along here, as the aluminium cuts through the magnetic field, eddy currents are induced. By Faraday's law, the rate of change of the magnetic field being cut is proportional to the EMF induced, and thus a larger current will flow. But by Lenz's law, that is in the opposite direction, the current flow, to the magnetic field that's producing it, and so we see effectively magnetically braking. What is also quite interesting is that if I use this, I can cause this to move along without touching it, and this is the form of what is called an induction motor. So an induction motor is a brushless motor that in effect can get movement, but you wouldn't do this. You would obviously use a changing magnetic field, usually on an AC coil. But what's quite nice is just to show you the rate of change of braking, or the braking force, is greater when it's spinning faster than when it's spinning slower. Quite a nice one. Again, so I have a runway and a very low friction cart, on there, and an aluminium block. Neodymium magnet. Neodymium, is obviously with aluminium. It's not magnetic, but if I move this along, it is inducing a current in it, which opposes the change producing it, and you can see if I get it moving, I can brake it with this, or if I pull it along like this, it's quite nice to show that you can move along from there. Also, what's quite nice is you can actually feel Newton's third law acting on your hand as you move the magnet across, which is really nice to show. Okay, so you can have students do this and show that from there. Nice one. The magnetic ball. Okay, you can usually get these from somewhere like Amazon. They're often sold as executive toys, sort of thing. So what we do, okay, is we drop the magnetic ball into the copper, and we see it induces an EMF and a current flows because there's a complete circuit, and it passes through very slowly due to Lenz's law. Above, okay, because you can see how slowly it moves, if I drop it through, it appears to be falling much slower than if I was just to regularly drop it. Again, as I show it dropping through, it's very smooth as it goes through.